In the previous video we looked at evidence for light behaving as a wave in Young's double slit experiment. In this video we're going to have a look at how light is produced as a wave. In order to do that we'll actually need to refer back to topic 3.2 on electromagnetism, both in terms of electric and magnetic fields, and we'll also sort of touch on electromagnetic radiation. Just to make a bit of a point here, when we're dealing with light as a wave, we're really looking at the way that the wave properties are apparent, so things like the wavelength, the frequency, wave speed. If we're looking at electromagnetic radiation, we're talking a little bit more about energy. So there is a link between the two. Sometimes the two terms electromagnetic wave and electromagnetic radiation will be used interchangeably, but just be aware that we're basically talking about the same thing when we use those two terms. Now, in order to make sense of this, we need to first of all briefly refer back to electric fields. And an electric field surrounds an electric charged object. So hopefully that's something that you can recall fairly easily. And we're going to change the way that we're looking at this scenario a little. So previously we looked at the fact that if we have a charge, in this case if we'll treat it as a positive charge, we'd have an electric field that would radiate out in all directions away from that charge. So we could represent the electric field around that charge looking something like that. Now, in dealing with light as a wave, we're not really interested in that view of the electric field. We're instead interested in more the what's happening at particular points in the region around that charge. So we're going to consider some points that are some distance away from the charge, and if we look at the electric field in those regions, we would see that they look something like this. And notice they're getting smaller as we get further away, because we know that the electric field strength decreases with distance. And so we'd have something that looks a little bit like that. So those arrows there representing the electric field at each of those 3 points. Now, if the charge moves to a different location, that's going to affect the direction of the electric field. So the direction of the field will also change. So if we were to consider this charge, let's say that it moves up and to some new position up here, I'll just do that as sort of a dashed line, we'd see then the electric field at each of these points is going to be directed in a different direction, because that the direction of the direction from the charge will be slightly different. If then the charge was to oscillate backwards and forwards, so if the charge was instead to then move down this way and then kind of continue to swing backwards and forwards between those two positions, what we would see is that that electric field is going to change backwards and forwards between those particular directions. So changing the position of the charge, we can change the direction of the electric field. Now, to take this a bit further, if we look at large distances from the charge, the component of the field that's parallel is not really going to change all that significantly. So we can basically ignore that parallel component. So that parallel component in this particular case is sort of across the screen to the right. So you can think of it as being horizontal. That's not really going to change. And so the can be treated as being a negligible change. And instead it's going to be the perpendicular component. So that's the component that we're going to be really interested in. So the perpendicular component will change. So that means that if we look at the region around this particular point here, let's call it point P, you can see that initially the horizontal component stretches out to this point here. Now, I haven't really drawn this to scale all that well, but you can see that there's not all that significant a change in the horizontal component in that particular direction. Likewise, there isn't a significant change in the parallel component for when the direction changes in the downwards direction. However, you can see that there is a fairly significant change in the direction of the perpendicular component. So you can see there that it's pointing up in one orientation and down in the other. So we get some fairly significant changes in the perpendicular component, but not really much of a change in the parallel component. So if we look at that point P, and we're going to plot the vertical component at point P, so the vertical component of the E field, and consider that over time, what we would see as the charge oscillates is a graph that looks something like this. So we would have, on the vertical axis, we're looking at the vertical component of the E field, and the horizontal axis is our time. The E field is going to vary in this sort of fashion. So you can see it's very much that sort of wave nature. Now, to make it a little bit clearer, I'm just going to draw some lines here to represent the direction of the size of the vertical component at different points in time. It'll become apparent why we're doing that when we start to look at the next little bit that we need to deal with. And so we end up with a wave that looks like that for the electric field. We also saw in topic 3.2 that a moving charge produces a magnetic field. So in this situation, we're going to see that not only is the electric field going to change, we're going to see a change in the magnetic field. So if we have an oscillating charge, so by oscillating we mean that it's moving backwards and forwards, an oscillating charge also produces an oscillating magnetic field. And we know then that the direction of that magnetic field is important as well, and the direction is perpendicular to the electric field. So to take that graph above a little bit further, I'll just reproduce it here first. So we need to now add another axis that's perpendicular to the electric field. So I'm going to draw that through this way, and this is going to represent the magnetic field. So you can think of it as being the x-axis is time, the y-axis is the electric field, the z-axis that's sort of coming out towards you is the magnetic field. Now the shape of this one's a little bit tricky to draw because we're trying to represent a three-dimensional diagram in 2 dimensions, so the shape of it might look a little bit unusual. I'll try and explain again with the use of the arrows here. So the strength of the magnetic field is going to change in a perpendicular direction. So instead of it being up and down, it's now sort of into and out of the screen. So you can think of that as being sort of a flat horizontal plane instead. So there's the changing electric field with the changing magnetic field. Hopefully now you can see with that diagram the wave nature of light, so the oscillation of the charge causing the oscillation in the electric and magnetic fields. We could talk about the wavelength of the light there, we can talk about the frequency, the amplitude as well. So lots of different properties about the wave nature of light that we can deal with by considering the electromagnetic wave. Another important one to mention here as well is that the wave speed of an electromagnetic wave relates to the speed of light. And this is for any electromagnetic wave, so whether it's visible light or infrared, ultraviolet, X-rays, gamma rays, radio waves, and in particular we're going to deal with in a vacuum, as that's where it's the fastest. That value is given as the speed of light. So all electromagnetic waves travel at the same speed in a vacuum, and the value that we use there is the speed of light, and the symbol that we use for that is c. The value for C is 3.0 by 10 to the 8 meters per second. I think if you look in the data booklet, it's only got 3 by 10 to the 8 meters per second. If you go to a little bit more detail, it's actually 2.99728 or something like that by 10 to the 8 meters per second. But if we round it off, 3.0 by 10 to the 8 meters per second is close enough. As I mentioned, that applies to all electromagnetic waves. In the next video, we'll have a little bit more of a look at the distribution of electromagnetic waves from particular objects known as black bodies, and that will then lead us into the particle model of light.